Okay, hello. Now we'll do the part two of our probability problems. These problems deal with random variables, which is chapter 6 in our textbook. And so some of these problems tend to be some of the more confusing problems, some of the more missed problems we have. But I think if you try hard, you can figure these out. It certainly may take some practice. I find that probability is one of the main things that people have to practice to review themselves for the AP exam, and I'll certainly be glad to help you out in any way I can in that regard. So let's look at context 4 here. Of course, the first 3 contexts we did in the previous video. But anyway, so this one says the number of pets that are in each household in a city are shown in the discrete random variable below. So a discrete random variable just means, discrete means it has a countable number of outcomes, either 0, 1, 2, or 3. So this is saying 30% of the households have 0 pets, 20% have 1, 40% has 2. Now, and so there can be some relatively simple questions asked here. Now, you need to realize the probabilities, to be a probability distribution, the probabilities have to add up to 1. Okay, so when you add these up, those add up to 0.9. So this has to be 0.1. And so sometimes it'll ask you a really simple question. It'll say if you randomly select a household, what's the probability that it has 2 pets, and that's just 40%, or what's the probability that has at least 2? So that would be 0.4 plus 0.1, which would be 0.5. And so I didn't include any of those in the examples here. But anyway, one of the more missed things is when they give a conditional. All right, so what's the probability that a household has at least 1 pet, given that it has at least 3? So the probability at least 1 pet, so that would be that x is greater than or equal to 1, given that it has, oh, I'm sorry, I said that backwards. What is the probability that has exactly 3, given that it has at least 1? Okay, like that. And so that is our notation there. And then, like we talked about in that last video, a conditional probability is the probability of both those things. The probability that x is equal to 3 and that x is greater than or equal to 1, over the probability of that second part, which is the probability x is greater than or equal to 1. Well, the probability that x is equal to 3 and is greater than 1, what's the easier way of saying that? That's just saying that x is 3. And so that's going to be 0.1 over the probability that x is greater than or equal to 1, and that's going to be 1, 2, or 3, which would be 0.2 plus 0.4 plus 0.1, so that's 0.7. So it's 1/7 is, in essence, the answer to that. So it's, 0.1 over 0.7, and that is equal to approximately 0.1429. So like that. So in other words, with random variable problems, the probability of one thing given another, it's always just going to be the probability of that over the probability of that. So keep that in mind in regards to random variable problems. And so let me erase this because I want to use that space up there for kind of the next thing. All right, so the next problem that it asks, what are the mean and standard deviation of the number of pets? Now, in a random variable situation, that's the next big section in our formula sheet. So here's our formula sheet, descriptive stats, and then there's the 2 big probability formulas from chapter 5. And then here is the formulas for chapter 6. And for a discrete random variable, the mean, otherwise known as the expected value, that'd be the other way of asking it, is equal to the sum of every x times every p. Okay, and then there's the formula for the standard deviation. It's a little more complicated, but there it is. So to find the mean, and there's also a shortcut with your calculator. So to find the mean, you just multiply each of these. That times that would be 0.3. So that would be 0.3. That times that would be 0.2. That times that's 0.8. That times that is 0.3. So I'm sorry, 0 times 0.3 is 0, okay? So you add those up, and so that would be 0.2 plus 0.8 plus 0.3, and so that's 1.3. So that is the mean of 1.3. Now the standard deviation. So our formula for standard deviation, as I just showed you, is this. It is, you take every x, you subtract the mean, which is 1.3, you square it, multiply it times its probability, and then add them up, and then take the square root. And I know that's a bit tedious, but it's happened on the exam before. And so what we would do if we're finding the standard deviation, we would subtract 1.3 and square it, okay? So that would be 1.3 squared and then times 0.3. And when you do that, in this case, you would get 0.507. And then we do it with 1. 1 minus 1.3 squared and then times 0.2. And so that would be So that would be 0.018. Then you say 2 minus 1.3 squared times 0.4, which is 0.196. It's really not hard. I mean, it's really arithmetic, except that it's just really tedious. And then 3 minus 1.3 squared times 0.1. And so that, in fact, is equal to 0.289. So then you add all those up. You add all those up, and that gives us the variance. So the sum, that gives us the variance, which is 1.01. Okay? And then, of course, the variance is the square of the standard deviation. So the standard deviation is the square root of 1.01. And so that is equal to like 1.004988. So that is 1.004988. Okay. Now, having said all of that, you could use your calculator, which is the quickest way of doing it. And so using with your calculator, what we can do is we can put the number of pets in list 1 and then the probabilities in list 2. So if we go stat and edit, so I will clear these out. And in list 1, we put the number of pets 0, 1, 2, and 3. Then in list 2, we put the probabilities 0.3, 0.2, 0.4, and 0.1. So those are, in essence, our frequencies. 0 is occurring 30% of the time, 1 is occurring 20% of the time, and so forth. So now what we can do to find the mean and standard deviation of this distribution is to go stat and go calculate one variable stats. And our list is list 1. Our frequencies, in other words, our probabilities, are in list 2. So I go second, list 2. This is the only time all year we put anything in the frequency list. Every other problem the whole year, make sure your frequency list is blank or it has a 1 in it, or you're going to get errors. Okay, so anyway, we go calculate, and so we have our mean is x bar in this case, and then our standard deviation is sigma. And that's also the only time we're going to use that sigma on your calculator. So that's certainly the quick way of doing that. But anyway, okay, not to belabor the point there, but maybe I did. All right, so anyway, so the next group of problems, deal with a uniform. Now, we have continuous random variables. Discrete random variables have a countable number of outcomes. So in regards to people, a discrete random variable would be, like, let's say the number of siblings they have, or the number of cars their family owns, or the number of the number of AP classes they're taking. Things that have a countable number of outcomes. Continuous random variables can take any value in an interval. So it's like people's height or people's weight. It could be 157.268 pounds. So most of the time, if it has decimals, then it's continuous. But anyway, so the next sort of problem is when you have a uniform. Uniform means it's going straight across. Okay, it forms a rectangle. So it says the times that people in a city spend watching TV each week follows a uniform distribution from 0 to 9. So I'll just draw that right up here. And so I'll just go 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And so, and uniform just means our distribution is going straight across, right like that. All the values occur equally. So, every point in this rectangle represents a time. And so, like, one person spends 1.27 hours, and so that'd be a point like right there. What's the mean? All right, so the mean is, now the thing about it is, the median is the number in the middle. Well, and in this case, if you look at this, if you say, well, what's the number in the middle? If you just say 9, 9 divided by 2 is 4.5. So 4.5 is halfway to 9. So that is the median is the point that divides it, is 50% is to the left and 50% is to the right. And if you count these over, you've got 4.5 on each side. So that is definitely the median, 4.5. Because this distribution is perfectly symmetrical, the mean and the median are the same number. There would be no other way to calculate the mean in this situation. So they're both 4.5. Now, what is the interquartile range? So the interquartile range, so that is going to be equal to Q3 minus Q1. Well, Q3 is the 75th percentile. And so what we can say is, well, what is 75% of the way from 0 to 9? So if we go 0.75 times 9, and so that would be 6.75. So that is 6.75. So that's like about right here. Okay, that's like about right there. And then what is the first quartile? It's the 25th percentile. So if I go 0.25 times 9, that would be a quarter of the way to 9. So that's 2.25. So that's about like right here. So the interquartile range is in essence the middle 50% of values. Okay, and so it would be, so our Q3 is, so the IQR is equal to 6.75 minus 2.25, and that in fact is equal to 4.5. 4.5, and so the middle 50% of our data is between there and there. So anyway. So that's how you do that. All right, and so if you randomly select one of the times, what's the probability to be more than 4? Well, the probability to be more than 4, you say, well, what's the area that's greater than 4? Well, the area that's greater than 4 is going to be, 1, 2, 3, 4, 5. So that is in essence going to be 5. All right, and then what's the total area of this thing? And I like to sort of assume that the height of this is 1 just to make my math easier. But the area of the whole thing is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 5 ninths, which is 0.5 repeating. So that's how you do that. So the probability of these continuous random variables is in essence the area of what's given over, or the area of what's asked for over the total area. All right, and then we have this. If you randomly select one at a time, what's the probability to be more than 7 hours given it's more than 3? So what's the probability more than 7 given that x is more than 3? Okay. Now our little formula, just like what we just had, that's the probability of both of these things, that and that, over the probability that x is greater than or equal to 3. All right. Well, what's the easier way of saying that something is greater than 7 and it's greater than 3? Well, it's just saying that it's greater than 7. So greater than 7 in this case, well, from there up, that's 1, 2. So it'd be 2. What's the area greater than 3? So that's going to be 1, 2, 3, 4, 5, 6. So it's 2, 6, which is 1/3. 0.3 repeating. So that is uniform sorts of problems. Okay, now let's deal with some normal problems. So this one says this: the weights of the bears that live in a large forest vary approximately normally, with a mean of 400 and a standard deviation of 30. What bear weights would be considered outliers? Now, there's a number of normal problems that deal with normal CDF, and I'm not going to get into those because we've sort of done a lot of them as we've, and so I just wanted to, but I wanted to sort of review things I thought that really needed reviewing. So what would be considered outliers? This would certainly be one of the tougher problems we have. Remember, outliers are anything that is less than Q1 minus 1.5 times the IQR, and so you have to memorize that, or anything that is greater than Q3 plus 1.5 times the IQR. Okay, and remember the IQR is equal to Q3 minus Q1. Now, so in other words, in order to find outliers, we need Q3 and Q1. How do you find Q3? It is the 75th percentile. So what we will do is we'll do inverse norm of 0.75. So that's what we do. So we do second distribution and go down to inverse norm. So we do inverse norm of 0.75, and then our mean is 400, and our standard deviation is 30, and then we go down, and so that's that. So it's 420.235. So it's 420.235 minus Q1. Well, what is Q1? It's the 25th percentile. So we go second distribution, inverse norm of 0.25, mean of 400, standard deviation of 30. We use left area for this, and you do paste, and then we do calculate, and it's that. So it's 379.765. So it's 379.765. And so that's Q3 and Q1. So we subtract those two guys, and let's see what we get. So if I say 420.2347 minus the answer like that, so it's 40.469. 40.469. That is our interquartile range. And now we can just enter this stuff into this formula up here. So anything less than Q1, which is 379.765, and then minus 1.5 times that, 40.469. And so that would end up being, so 379.765. And so if I just go times 1.5, so it's 60.704. So minus 60.704. Anything less than that. So it ends up being less than, it ends up being 319.06 roughly. Anything less than that would be an outlier. Or greater than 1.5 times IQR. Well, that would be 420.235, plus 1.5 times 40.469. Okay, and when you do the math there, that ends up being 480.9387. So anything less than that or greater than that would be an outlier. That's one of the tougher problems we have. So finding the outlier for normal curve. But that's it. That's how you do it. All right. So then we've got this. It says the weights of the tigers that live in a forest of number 20 vary approximate normal with a mean of 430 and a standard deviation of 20. If you randomly select one of the bears and one of the tigers, what's the probability that the sum of their weights will be greater than 870? All right, so in essence what we're doing is we're adding together two normal curves. And we can do this, and we can do the things with standard deviations if they're independent. In other words, if the occurrence of one is in no way associated with a change in the occurrence of the other. And I would say that they are probably unrelated. But anyway, so we want to know the probability their sum. So we're going to go, so these are bears. So we're going to go look at bears plus tigers. We have to add together the two distributions. When you add together the two distributions, you add the means. Okay, the mean here's 400, the mean here's 430, so that is going to be 830. But the little trick here, when you add distributions, you cannot add the standard deviations. Okay, you can add 30 and 20. You have to add the variances. And so the variance, the square of the standard deviation for the bears is going to be equal to 30 squared, and that's equal to 900. And the variance for the tigers, is equal to 20 squared, and that is equal to 400. Okay? All right, and so then you would say we can add these two variances to get 1,300. So the variance of the bears plus the tigers is equal to 900 plus 400, which is 1,300. Therefore, the standard deviation is the square root of 1,300. So it's like the Pythagorean theorem. You just square them and add them and take the square root. And then, so there's our distribution of bears plus tigers. Now we can find the probability that if you randomly select a bear and a tiger, that their total will be more than 870, and we do normal CDF. Normal CDF from 870 to infinity. Our mean is 830. Our standard deviation is the square root of 1,300. Of course, to show your work, lower bound, upper bound, mu, sigma. And when you do that, let me remind you on your calculator, normal CDF, so you go second distribution, which is the VARS button, of course, and we'll do normal CDF, and we are going from 870 to infinity. And so then my mean is 830, and then my standard deviation would be the square root of 1,300, like that. And we got ourselves an answer, 0.1336 approximately, 0.1336. So that's how you do that. All right, so then the next question is this. If you randomly select one of the tigers and one of the bears, what's the probability the bear weighs more than the tiger? Whenever you're asked to compare two normal curves, you're going to subtract them. What's the probability this is more than that or this is less than that? You're going to subtract them. So bears more than tigers, I'm going to say bears minus tigers. So bears minus tigers, you can subtract the mean. That would be 400 minus 430, which would be negative 30. But the thing that may be a bit counterintuitive, whenever you combine curves, whether you add them or subtract them, you still add the variances. Okay, you're still going to say 900 plus 400 because you're in essence combining the two variabilities of the situation. I'm not going to explain that thoroughly, but just trust me on it. And so there you go. So that's our new distribution. And so the question is, okay, if the bear weighs more than the tiger, that means this expression is positive. If bear is more than tiger and you subtract them, it means it's going to be a positive number. So this is in essence asking what percent of this bears minus tigers curve is greater than 0. And so we'll do normal CDF from 0 to infinity. Those would be the positive numbers. If it had said, what's the probability of tigers more than bears, then you do the negative numbers, negative infinity to 0. But anyway, this is negative 30, and it'll be the square root of 1300. So that is my lower bound. That is my upper bound. That is my mu. That is my sigma. And when you do that, so what the heck, let's do that. And so you do second distribution, normal CDF, and we are going from 0 to infinity. So I do a 0 to infinity, same mean and standard deviation. No, mean is negative 30, sorry, negative 30. And by the way, once again, whenever you hit the negative button, hit the negative button, not the minus button. That would cause an error. All right, and so then go like that, boom. And there it is, 0.2027, approximately 0.2027. And I think that would make sense because in general, you know, the tigers are weighing more than the bears. And so we're expecting it to happen less than 50% of the time that if you were to randomly select, you get a bear weighing more than a tiger. That seems reasonable. And then we've got this. And if you randomly select 3 tigers, what's the probability their sum will be more than 1350? Now, this is different than, so 3 tigers, getting 3 different tigers, it's different from getting 1 tiger and multiplying it by 3. In other words, if you multiply a distribution by 3, okay, so and once again, our tiger distribution is normal, approximately, has a mean of 430 and a standard deviation of 20. Now, if you get 1 tiger, and multiply it by 3, you can just multiply the mean and standard deviation by 3, okay? That's a part of a transformation. But if you get 3 different tigers, and add them, that's a different thing. In other words, you've got to add together the distribution 3 times. 1, 2, 3. And when you add together the distributions, you can add the means, but you can't add the standard deviations. You got to add the variances. In other words, we have to multiply our variance by 3. So our variance for the tiger is 400. And so for 3 tigers, it will also vary normally, and you can multiply that times 430 times 3. That's 1290. And then this would just be, we have our variance, so our variance for our 3 tigers is going to be 3 times 400, and that's 1200, and so our standard deviation is the square root of that. And so, anyway, so what's the probability that that's going to be more than 1350? So you go normal CDF, 1350 to infinity, our mean is 1290, our standard deviation is the square root of 1200, like that. So that's my lower bound, that's my upper bound, that's my mean, that's my sigma. And when you do that, you would end up getting 0.041632 approximately. Now look, these are some of the hardest problems in the world of AP. They're the most missed problems all year. Of the whole AP Stats curriculum, these are the hardest mathematical problems we got. And so there you go. But anyway, all right, and then lastly, we have binomial and geometric situations. So now a binomial situation is when in essence you've got a probability given to you, then you have a number of trials and you're asked to find a probability of number of successes. So it has to be a binary situation, a success-failure situation. You have to have a fixed number of trials, and this probability can't change throughout the problem. Okay, so anyway, and if you got that, you got in essence a binomial situation. So this says 23% of dogs in a city have fleas. You randomly select 10 of them. Find the probability that exactly 3 of 10 have fleas. So you need to recognize this as a binomial situation. All right, a given probability, a fixed number of trials, and a number of successes. Now, it's a binomial PDF problem. I'm going to show you that. The formula that is on your formula sheet, all right, for a binomial situation. It's right there. For binomial, that is, and you got to be able to recognize that formula. Okay, you got to be able to recognize it, certainly. You can use binomial CDF and binomial PDF to get an answer, but anyway, so I want to show you the formula first. So it's going to be 10 choose 3, and then we've got 3 successes. So 0.23 is the probability of success. We got 3 successes, and that means we have 7 failures. And so that would be the probability of failure is 0.77 to the 7th. So if you got a 23% chance of success, it means you have a 77% chance of failure. And so this is, in essence, what's the probability that in 10 trials, you're going to have 3 successes, 7 failures, and that's the total number of different ways you can, in essence, rearrange them. All right, and so the way you would do that with your calculator is you would go 10 choose 3. The way you can find that is the math button. If you go math and then probability and then there, 10, and we go hit that, and then we go 10 choose 3, enter. And so we say times 0.23 to the power of 3. That little up arrow button raises it to the power. And then times 0.77, and then the up arrow to the 7th power, like that. And we got an answer, 0.2343. So that's approximately equal to 0.2343. So that's using the formula. Now, but you can use certainly binomial PDF. And so binomial PDF is in your distribution menu right there by the VARS button. So you go second distribution, and you go binomial PDF. PDF is for 1 point. Binomial CDF is cumulative for a number of points, for the probability of a certain value or below it. But this is just for 1 point. This is exactly 3, so it's PDF. And so my number of trials is 10. My probability of success is 0.23. And then my number of successes is 3 successes, 3. And so we go like that. And so in some calculators, by the way, immediately take you to that screen. So you just put N, P, and X. Put it in alphabetical order and put commas in between them. So you go like that. So it's the same answer. Okay. And to show your work, you certainly could write that, but you can write binomial PDF, but you have to clearly label what the numbers are. So our X is 10. Our probability of success is 0.23. And then, I'm sorry, our N is 10. My bad. Our N is 10. And then our X is equal to 3. So it goes alphabetically. So yeah, don't get the letter, but make sure and put the letters. And then that would be considered showing your work there. All right, what's the probability that at least 4? Well, let's think about this. So all right, when you have 10 trials, the number of successes you could possibly have, you could have 0 successes, you could have 1, you could have 2, 3, 4, 5, 6, 7, 8, 9, and 10. Those are all of our possibilities that could happen. When you select 10 dogs, you get one of those numbers. Now, so the probability of at least 4 is everything from here on up. And back in the old days, what we would have to do is we would have to use this formula a number of times to figure this out. But what we can do is we can use binomial CDF. All right, binomial CDF means cumulative. And the word cumulative in math, it means the probability of something or below it. It is what is accumulated from the left. So we can use binomial CDF to find a value. All right, realizing these probabilities are going to add up to 1. So if I can find the probability of 0, 1, 2, and 3, and then subtract it from 1, I'll have the answer to this problem. So the probability that X is going to be at least 4 is in essence 1 minus the probability that it's going to be less than or equal to 3. And so that is going to be 1 minus binomial CDF, where our N is equal to 10, our P is equal to 0.23, and our X is equal to 3. And so when we do that, we would go second distribution, then go down to binomial CDF, right there, option B. And so our number of trials is 10, our probability of success is 0.23, and X, our number of successes, is 3. So this is the probability of 3 or less successes, and so it's that 0.8206. So that is equal to 1 minus 0.8206, and that in fact is equal to 0.1794. Yeah, and so that is that. So that's the answer to number 25. So all that goes with 25. So there you go. All right, what are the mean and standard deviation of the binomial situation here? All right, so the mean for binomial, okay, there's your formula. There's the mean, there's the standard deviation. The mean is n times p, and the standard deviation is the square root of n times p times 1 minus p. So our mean, otherwise known as our expected value, so our mu is going to be equal to n times p, so that is just 10 times 0.23, and so that's equal to 2.3. Right there. And our standard deviation is the square root of n times p times 1 minus p. And when you do that, you would get like 1.331 approximately. And so that's how you do the mean and standard deviation of a binomial situation. And then the last thing we're going to talk about is a geometric situation. A geometric is when you're concerned with when is your first success. When is your first success? You're just looking for one dog that has fleas. You just need one to test something out. I don't know, but you just need one of them. You don't need like 3 successes out of 10. You're just how many dogs do you have to go through? And so this is sort of the premise of that. And so what's the probability that the first dog you encounter with fleas will be the 6th one? Well, if your first success is on the 6th, what happened on the first 5 trials? They were failures. And so our probability success is equal to 0.23. Okay? Well, if that's our probability success, that means our probability of failure is 0.77. And the probability of that happening 5 times is to the 5th power. And then times your first success on the 6th one. So this represents the probability that you have 5 failures and then a success on the 6th trial. In other words, your first success is on the 6th trial. And so let's see what that is. And so we'll go 0.77 to the power of 5. And then times 0.23, and so that's equal to 0.0, so that's equal to 0.06226 approximately. So that is that. And then lastly, what is the mean of the number of dogs you would expect to encounter until you meet the one with fleas for the first time? When are you expecting your first success on average? And in the geometric situation, that is that. It is just 1 over p. And then, by the way, there's the formula for what I just said. And what we just did, by the way, is the probability that you're going to have that your first success will be on the X trial is just that. But anyway, and there's the standard deviation right there for a geometric situation. It's just the square root of 1 minus p over p. But in this case, the mean, otherwise known as the expected value, is 1 over p. So it is just 1 over 0.23, and that is approximately equal to 4.3478. So on average, in the long run, we would expect to have to go through that many to find a dog with fleas for the first time. That's it. I know that's a lot of stuff, but that's reviewing all the major concepts in random variables. And so see if you can give that that worksheet a shot, and send me any questions you have. And thanks for watching the video.